These are, remember we spent a lot of time doing recursive backtracking, right? And today in 1090 logic class, we actually mention recursive backtracking. And so why don't we mention it a little bit here? All right, so there's some big statement here that I want to prove, right? If we're doing logic, there's some statement I want to prove that's true or not true, right? And how do I do it? Well, I don't know how to do it. So what we often do is we branch. We might branch on the variable of x being 0 or the variable of x being 1. We might branch on some crazy beta statement being true or that crazy beta statement being false, right? And then when we're down here, I kind of pretend that the little bird has told me that, right? Why? So that I trust it and I really embody the fact that these things are true, right? And then I go off, and with this extra information, right, I do whatever I want to do with alpha, right? Prove it's true or solve the problem or something. And then I backtrack and I do the same, pretending that these things are true, right? So recursive backtracking is I have some problem to solve. I'm going to branch on something, right? We might branch on, do I put that, if I'm doing the knapsack problem, I might branch on, do I put the last object in the knapsack or not, right? If I'm solving the staircase problem, I might branch on, do I take 1, 2, 3, 4, 5 steps, right? That would be, I have a lot of branches. How many steps do I take, right? Does that make sense? All right, so it turns out I have some slides here on recursive backtracking anyway, all right? Oh, and we're not covering dynamic programming, but dynamic programming takes this recursive backtracking algorithm and says, hey, there are too many friends all solving the exact same subproblem, right? Imagine we're doing Fibonacci numbers, right? I'm doing Fibonacci 10, I get 9 and 8 to be done. What does 9 do? 9 gets 8 and 7, right? Right there we have 2 8s, right? Imagine how many 3s we have, right? So dynamic programming just cleans that up so that nothing is solved more than once, all right? But here, suppose you, right, then you might say, well, why do we do this recursive backtracking? I mean, it usually is exponential time, but suppose that's what you want to do. Suppose you want to do it because you don't have a faster algorithm and you're willing to go over all these solutions, right? It really does take exponential time, right? Why does it take exponential time? Because I branch over the value of x1, and my friend branches over the value of x2, and then his friend branches over the value of x3, right? So then you get this tree of where you branched over all n of your variables, and the size of the tree is exponential, right? So, right, then you say, well, why do you want to do this? Well, sometimes it's the cleanest way to do it. Suppose, for example, we want to, we're given a tree like this, and I called it it's an acyclic tree. You'll note all the edges go down, right? And that makes our life a little easier. And what I want to do is I want to list every path, right? And first off, how many paths might there be? Right? If I have n nodes, 2 in or 2 to the n? 2 to the n, right? Because you can imagine every time you hit a node, you have 2 or 3 choices, right? So it's exponential in n, where n's actually not the number of nodes, it's the height of the graph, right? Because every graph you're branching, right? So it's exponential, but it's still complicated, right? And if you say I want to print out all exponential number of them, how might I do that? Well, you branch, right? You say the little bird sort of tells me which edge to take first. And so that's where I'm doing this branch. And then what do? Is I ask my friend for the best, all the paths from V1 to T, right? Or maybe I ask them not for all of them, I ask them for the best one, right? And then what does he do? He can either send me them all, or he sends me the best one, or he sends me, right? He sends me something about them. And then I add back on what I call the bird's answer, right? I add back on that first edge. And now I have all these paths. And what are these? These are all the paths from S to T consistent with the bird answer of taking that first edge. Right? Does that make sense? And if the friend told me which of these is best, and then I add this edge onto his best path, then what will that give me? That would give me the best path from S to T of those that go through that edge, right? Because we've only considered the ones through that edge. Well, then I backtrack and I consider the next, right? Oh, here's the code, right? We're looping over all the edges SV, right? And for each, we recurse. Here's our recursive algorithm. I guess this is called, we're recursing, starting at V, going from V to T, right? So these are all the paths, or the best path from V to T. And then we add on this edge from S to V, right? And then we do it for the next edge, and the next edge, and the next edge, right? Oh, I guess we don't have a next one. But, and then here's a really, look at this, just this graph right here. You can see it has an exponential number of paths, right? Because each little diamond, you got to choose whether to go left or right. Right? Everybody follow that?